Hey everyone, in this video we're going to learn how to translate parent functions, which can be broken down into two types of translations, horizontal and vertical. And we're going to start with the vertical translation, which is adding or subtracting a constant value to the y-coordinate of each point on the graph of a function. Now think if I gave you a set of points and I told you to add the same number to every y-coordinate. Each point would move up on the graph. So we should expect our graph to move up, or if we subtract, move down. So let's see if that's the case. And we're going to do so by comparing y equals x squared and y equals x squared plus 2. In red, we have the graph of the parent function, y equals x squared, and in blue, we have the graph of the translated function, y equals x squared plus 2. If we take the vertex of the parent function and compare it to the vertex of the translated function, we can see that's been moved up 2 units. Now, could there have been another transformation that moved our vertex? Well, we've talked about scaling already, which multiplied the x or y value by a constant value. And if the vertex is 0, 0, there's nothing we'd be able to multiply that would give us 0, 2. So scaling is out, and the only way I see to get 0, 0 to 0, 2 would be to add 2 to the y-coordinate. But let's see if that rule follows for all of the points on the parent function. For instance, if we take the point 2, 4, if we add 2 to the y-coordinate, we should get the point 2, 6, which we do. If we take negative 2, 4, add 2 to the y-coordinate, we should get negative 2, 6. And we can do that for every point on the parent function in relation to the translated graph. If we look at our table of values, we'll notice the x values in each table are the same. And when comparing the y-coordinates, if we take the y values of the parent function and we add 2 to each one, we get the y-coordinate of the points on the translated function, y equals x squared plus 2. So in this case, for any x value, what do we add to the y-coordinate of y equals x squared? To get the y-coordinate of y equals x squared plus 2, we're going to add 2 to each y-coordinate. Okay, so they'll have the same x value, the y-coordinate from the parent function, add 2 to it, we'll get the y value of the translated function. Now what if it becomes subtraction? So if we compare y equals x squared and y equals x squared minus 2, so in red we still have the parent function, in green we have the translated function, y equals x squared minus 2. So if we compare the vertex of the parent function to the vertex of the translated function, we can see that it's been moved down 2 units. So let's see if that rule holds for all of the points. So in this one, let's look at 1, 1. If we move it down 2 units, it'd be 1, negative 1. If we look at negative 1, 1, move it down 2 units, we'd have negative 1, negative 1. So we can use the table of values to compare again. X's are still the same. And if we compare the y values of each function, we can see that the y values of the parent function, if we subtract 2 from each of them, we would get the y values of the translated function, which is y equals x squared minus 2. So for any x value, what do we subtract from the y-coordinate of y equals x squared to get the y-coordinate for y equals x squared minus 2? So we're going to subtract 2 from each y-coordinate. Okay, so x values stay the same. Subtract 2 from each to get the y-coordinate of the translated function. So there are the vertical translations. So we had a shift up in the first one and a shift down in the second. Now what do the horizontal translations look like? So a horizontal translation is adding or subtracting a constant value to the x-coordinate of each point on the graph of a function. Well, think of it this way. If I give you a set of points and I tell you to add a number to every x value, well, the points would all move to the right. And if I tell you, here's a set of points, subtract the same number from every x value, the points would move to the left. So let's see if that's what happens graphically. And we'll do that by comparing y equals x squared and y equals the quantity x minus 2 squared. In red, we still have our parent function. In pink now, we have the translated graph of y equals the quantity x minus 2 squared. So if we take the vertex, I'll use blue in this case, okay, the vertex of the parent function, and compare it to the vertex of the translated function, I can see that that vertex has been moved 2 to the right. Now let's take another point. Let's see if that's always true. So 2, 4. If we move that point 2 to the right, we would get the point 4, 4, which we do. Let's take the point, let's go up here, negative 3, 9. If we move that point 2 to the right, we should get negative 1, 9, which we do. So if we compare our table of values, we can see now the y values are the same, they're not changing. And if we're comparing the x values of the parent function, if we add 2 to all of those x values, we would get the x values of the translated function, which in this case is y equals quantity x minus 2 squared. Now let's think of that for a second. If I asked you to take a guess at what was happening to y equals quantity x minus 2 squared, I'm pretty confident most of you would have guessed 2 to the left. But we see that it was the opposite. Well, this brings us back to an idea that we talked about in scaling. The equation is always telling us how to get back to the parent function. So this is saying if I had the pink graph and I wanted to get back to the parent function, which is red in this case, then subtract 2 from all of your x values. Well, think about this arrow that I drew. If I did it in the other direction, that plus 2 would turn to a minus 2. So that rule, that idea, still is true. So what we talked about in scaling is still going to be the case in translations. Now, if you go back to the vertical, it was plus 2 and minus 2, and that seemed to match up well. But remember, that was on the other side of the equation. We were changing y values. To go back here, we were changing y values, but the minus 2 wasn't with the y in the equation. Okay, so that's something we'll talk about when we're done here. So for any y value, what do we add to the x-coordinate of the parent function to get the x-coordinate for the translated function? So we're going to add 2. So if that moves 2 to the right, what would move 2 to the left? We'll compare y equals x squared to y equals the quantity x plus 2 squared. And we can see, in red we have our parent function, in purple we have our translated graph, which in this case is y equals the quantity x plus 2 squared. If we compare the vertex of the parent function to the vertex of the translated function, we can see that's 2 to the left. Now let's take the point 2, 4. If I move that 2 to the left, we get the point 0, 4, which we do. If I take, let's take that same point, negative 3, 9, move it 2 to the left, negative 5, 9. So if we compare our table of values, again, the y values are staying the same. We can see that when we compared our points. If we compare the x values, if we take the x values of the parent function and we subtract 2, then we would get the x values of our translated graph, which in this case is y equals the quantity x plus 2 squared. And again, if I had just given you this equation, intuitively, you probably would have said it should move to the right. But we see on the graph, it actually moved to the left. Again, reiterate that idea. The equation is always telling us how to get back to the parent function. So if I had the purple graph, I would then add 2 to all my x's to get the parent function. Now, realistically, we know the parent function and want to get the translated function. So we're going to have to reverse the idea that the equation is telling us. So for any y value, what do we subtract from the x-coordinate of the parent function to get the x-coordinate of the translated graph? In this case, we're going to subtract 2. Now, I don't like having different rules, right? For the horizontal, it was opposite what our intuition would say. And if we look at the vertical, right, -2, it moved down 2. +2, it moved up 2. Okay, that's great, but I'd have two different rules. So let's treat this the same way we did with scaling. So we're going to rewrite the equation in this form. Y minus b equals f of x minus a. So anything happening to the x value is going to be a horizontal translation, and anything happening to the y value is going to be a vertical translation. Okay, so A represents the horizontal translation, B represents the vertical translation. If A is greater than 0, then we're going to classify it as moving to the right, and look back at y equals the quantity x minus 2 squared. We can visually see that it moved to the right. Again, opposite our intuition, but it's because the equation's always telling us how to go from the translated graph, in this case, back to the parent function. If A is less than 0, then we classify the translation as moving to the left. So that means A is negative, so if we subtracted a negative, that would become plus, and go back to y equals the quantity x plus 2 squared. We can visually see that it was moved to the left. If b is greater than 0, then we classify the translation as moving up. And if b is less than 0, then we classify the translation as moving down. That's because if we have y minus 2, well, I would then move it to the other side, and it would be plus 2 to the y values. And similar for our other case. Okay. This should also look similar to something that we've talked about this year. Okay. And what it should look similar to is that point slope form. Y minus y1 equals m times x minus x1. Right, that point slope form where we pulled out the point that's on the line and the slope. Well, that point we always said was x1, y1. Right, and we did a little work of understanding why that was the case. This is the same idea, but generalized now to all of our parent functions, not just our lines. Okay, so let's put some numbers in this to help us wrap our head around it. Determine the translation of each function in comparison to its parent function. So our first is y equals the absolute value of x minus 5. So our parent function is the absolute value of x. Let's get it so that this minus 5 is on the other side, so y plus 5 equals the absolute value of x. Okay, so if the equation is telling us to add 5 to the y values, then that means that we're going to subtract 5. So that means we're going to shift down 5. Now we can also create a shorthand notation the way we had for scaling. So we'll have a capital T for a translation of a comma b. So in this case, we have a translation of 0, -5. If we had a table of values and we're trying to graph this, we would add 0 to the x values and -5 to the y values. Next, we have y equals the cube root of x plus 1. So our parent function is y equals x, the cube root of x. And if it helps, we can think of this as the cube root of x minus -1. So our translation is -1, 0. We're going to add -1 to the x, 0 to the y. So this is going to be a shift left by 1. Okay. Next, we have y equals the quantity x minus 8 cubed. So our parent function is y equals x cubed. Now we have x minus 8. So the equation is telling us to subtract 8 from the x values to get back to the parent function. So to go forwards, which is what we want, we're going to do the reverse. We're going to add 8 to the x values. So our translation is going to be 8, 0. And that's going to be a shift. Well, if we add 8 to the x values, we're going to move to the right. So shift right by 8. And then last, we have y equals x squared plus 12. So putting it in our format. We have y minus 12 equals x squared. So our translation, nothing to the x's, so 0. And to the y's, if the equation is telling us to subtract 12 from the y's, then we're going to do the opposite. We're going to add 12 to the y values. So that means we're going to shift, let's see, if we add 12 to all the y values, that's going to move every point up. So shift up by 12. Okay, so individually, we've looked at down, up, left, and right in these 4 examples and able to isolate. The reason if nothing's happening to the x or y, it's 0, is because we're dealing with addition and subtraction. With scaling, we were talking about multiplication. So if nothing was happening, we want to multiply by 1 to keep everything the same. If a translation is adding and subtracting, well, we want to add or subtract 0 to keep everything the same. So looking at the difference now between translations and scalings, and that's going to be important as we put everything together. Last 2 examples. Determine how each function has been translated in comparison to its parent function. The first function, y equals the square root of x plus 6 minus 4. Our parent function is y equals the square root of x, and we're trying to figure out how that parent function has been translated to get this function that we've been given. First thing I'll do with the minus 4 is add it to the other side. So y plus 4 equals the square root of x plus 6. Now remember, the key idea we've been emphasizing is that the equation is telling us how to get back to the parent function. So if I had this graph already, to get back to the parent function, I would add 6 to x, add 4 to y. But our goal is to do the opposite. I want to go from the parent function to this graph. So our translation, so if the equation is telling us to add 6 to each x value, we're going to subtract 6 from each x value. And add 4 to each y value, then we're going to subtract 4 from each y value. Now we need to put this into words. So it's going to be a shift. If we're subtracting 6 from each x value, each of those points is going to move to the left. So shift left 6. And if we're subtracting 4 from each y value, then each point's going to move down by 4. So down 4. So here's an example with both a horizontal and a vertical translation. And again, we get to emphasize that point that the equation is always giving us the opposite of what we want. Next function, y equals f of x minus 11 plus 7. Our parent function in this case is just y equals f of x. So a general function. First thing we want to do with the plus 7 is subtract it to the other side. So y minus 7 equals f of x minus 11. So our translation, we're subtracting 11 from x in the equation. That means we want to add 11. And then subtracting 7 from each y, we're going to add 7 to the y values. So putting our translation into words, so we're going to shift if we add 11 to each x value, that's going to move them to the right. So shift right 11. And if we're adding 7 to each y value, then the points are going to move up 7. Okay, so key idea in this video is being able to identify the translation. Emphasizing that idea of the equation telling us how to get from the graph that we want back to the parent function. So we have to think in the opposite way. Now we'll take these translations and we'll practice graphing and writing equations. So if any part of this video confuses you still, go back and watch that specific part. Practice with this a little bit before moving into the next video. Click the Amazon link down below for my algebra workbook so you can practice on your own. Give the video a like, and before you go, click that subscribe button so you can see more videos just like this. Thanks for watching.